and there has been some related work regarding this consistent hashing, and these are some of the works. The using systems of several cooperating caches, fault tolerance, and scalability and aggregation of large requests will be achieved. And every client selects one primary cache in the system, and a request is sent to primary cache. And the request from the client goes to its primary cache. If the primary cache misses, instead of going directly to the content server, it tries to locate the resource. And in other cooperating caches, if it succeeds, a slow fetch of the resource from the content server is replaced by a fetch of the resource from a cooperating cache. Thus, the other cooperating caches serve as a second level cache, and it reduces the cost of misses in the primary cache. So the systems differ in precisely how data is located in the case of a primary cache miss. Some schemes broadcast a query to all other caches using multicast or UDP broadcasts, whatever. And besides consuming excess bandwidth with broadcast queries, the primary cache must wait for all cooperating caches to report misses before it contacts the content server. This can slow down performance on second level cache misses. Uh, the other schemes use the directories, like either centralized or repeatedly broadcast, to support local queries. And directory queries or transmissions also consume bandwidth, and centralized directories can become new points of failure, so they are not successful. And going on to our the cache resolver, the distributed web caching system that we developed, eliminates intercache communication and on a miss by letting clients decide for themselves which cache has the required data. So a directory based location scheme involves too much overhead to involve every browser, but a hash head scheme is easy to implement at browser level. So hashing provides several benefits over broadcast and directory based schemes, because a machine can locally compute exactly which cache should contain a given object. A unique cache suffices to get the object or determine that is not cached, decreasing network usage compared to other schemes. It also discovers misses and faster than the multicast schemes and must wait for all caches to respond. It avoids the maintenance and query overhead associated with the directory based schemes. And thus, prior schemes assume that each client always contacted one fixed primary cache, which on a miss contacted another caches to see if they had the page. We let the browser decide directly uh, which cache to contact. This removes the need for an intermediary cache, thus improving the response time. Basically, the main aim is to make it faster, and reduces the miss rate also. The miss rate is further reduced because we avoid making redundant copies of a page, and this leaves more space for other pages to be kept in the cache and hit. So there's maximization of memory, and we can improve the speed, and the misses are also reduced. So a similar proposal for like this is was proposed for the cache array routing protocol. It was used in Microsoft Proxy Cache. So there's a little difference, and the difference between our proposal and the CARP is the how our hash function is implemented. The current browsers do not have all the functionality needed to support such a scheme. CARP places all consistent hashing responsibility on the browser, which creates some drawbacks like we will be discussing. And the difference is we make unusual use of domain name system. It is a, like, we use it for the positive purpose, but it's a different kind of use. To support the browser's use of hash functions, it is used differently. In paper overview, now we describe consistent hashing in detail in section 2, and the implementation of our web caching system in section 3, and comparing our system with the other web caching systems in section 4, and positive aspects like fault tolerance and load balancing in section 5, and the conclusion in section 6. So our system is based on consistent hashing basically. um, Here we motivate the consistent hashing and describe its simple implementation basically. Next, the needs. The goal of our system is to let any client perform a local computation that maps a URL to the computer cache containing it. So such random distribution will be used inside our system. The It is the common institution, but that the hash functions, they are random. They tend to we distribute the hashing uh, hash functions randomly, so that we would reduce the effort that falls on each of the servers. So standard hashing has also drawbacks, but the random distribution will be intuitive and even mean that no one cache becomes responsible for handling a number of requested pages. So this load balancing feature of hashing, it is very highly desirable to any our application, basically the browsers, since disappropriately load cache will become the bottleneck for the entire system. So standard has caching has its own drawbacks when applied to a caching system like caching machines, because the caching machines might go up and down over time. They are not so dependent. So for suppose a natural consider if we add a 24th cache to the system, a natural change is to begin using the hashing to the system, like described the function. So the function will be like, suppose it's h dash u, it will be like 7u plus 4 mod of 24, because we added the 24th one. So this might cause some problems. If each view causes a URL to map a different cache, we will soon find out that each URL is stored in all caches, precisely the problem we are trying to avoid. And each item should be mapped to only a number of um, small number of machines, in such a way that all machines get roughly the same load of items. Okay, so consistent hashing. A simple consistent hashing satisfies the needs described in the previous section, which are the basic requirements, and some standard base hash function that maps strings to the range 0 to m, say. uh, they If we divide the servers in a circle, suppose 0 to m, then every URL is thus mapped to a point on the unit circle. At the same time, every cache in the system to a point in the unit circle. Now we will assign each URL to the first cache whose point it encounters, moving clockwise from the URL's point. So all the catch points can be stored in a binary tree, because and they are saved in a clockwise manner in the unit circle. So the clockwise successor to a URL's point can be found via a single search in the binary tree, because they can be represented in a binary tree, so the search will also be very easy. So this supports consistent hashing to n caches, and the order will be order of log n. So an alternative implementation is like breaking the circle into equal length intervals and grouping, and interval that is an alternative improvement. So the difference between our consistent hashing and CARP is CARP takes the linear time linearly in the number of caches, and it is much less scalable to large number of caches. Next, our analysis. The base hash function will map both URLs and cache points randomly to the unit circle. A cache will get stuck if with an item, if it is the closest cache to the item in some view. If the cache is far away from the item, then it becomes quite likely that in every view some cache is closer. So we will have a standard, like we will have a stability in the system. So even if there is an imbalance, the one of the server, it won't get um, any stress, like it it won't get too many requests from um, the requests that are left because of the server that was failed at that point of time. So this prevents the cache from being stuck with the item. It follows that only caches close to an item will have to hold it, and we can explain this with a theorem. Like if we consider with a system with m caching machines and c clients with an arbitrary set of half the caching machines. For example, if all the URLs are mapped for each of the points and all the conditions are set, then the unit circle, using a good hash function, it holds the following properties. First one is balance. In any one view, URLs are uniformly distributed over the caching machines in the view, which is basically the pre-requirement. And the load, over all the views, no machine gets no more than order of log c times the average number of URLs. It is because the whole design, it is very stable, so that um, there is no chance of imbalancing the whole system. So the load is um, distributed equally. And third one, the spread. No URL is stored in more than order of log c caches.